Part 2, the central limit theorem. So if samples of size n greater than 30 are drawn from any population with mean, mu, and standard deviation, sigma, lowercase, then the sampling distribution of the sample means approximates a normal distribution. The greater the sample size, the greater the approximation. So like that previous one that we did where it had like the bell shape and it was symmetric and everything else, that's a normal distribution if we were to create a curve for it. The good thing about though, the bigger the sample size, the more accurate that it's going to be, the more normal it's going to be, which is going to be great for us. So this is going to work for us for anything where n is greater than or equal to 30. Number 2, if the population itself is already normally distributed, weird emphasis, then the sampling distribution of the sample means will also be normally distributed for any sample size n. So it doesn't matter, it doesn't have to be greater than 30. If it's already normal, it's going to stay normal. In either case, the sampling distribution of sample means has a mean equal to the population mean. So that's what we just discovered. So no matter if it's greater than 30 or not, or normal or not, it's going to have the same mean. Then you also learned from the other one was that, go ahead and take a moment, read this. The sampling distribution of sample means has a variance equal to 1 over n times the variance of the population and a standard deviation equal to the population standard n divided by the square root of n. That's the same thing that you just did. I know it sounds complicated. Promise, it's really not that bad. So what that is saying is we're not really going to use the variance so much though. So I'm just going to focus here on the standard deviation. X bar, remember, is sample means, is the standard deviation divided by the square root of n. This is really where we focus a lot more than variance. And just the gist of number 1, they're saying if it's any population, so any population, and it looks kind of crazy or whatever is happening, then if the sample size is greater than n, it's going to end up looking like a curve like that when we do our little magic with the sample means. This is for n greater than or equal to 30. If it already starts off as normal, then for any n, it's still going to be normal. Pretend like that looks like a really good normal. Just imagine it. Close your eyes. Okay, let's get to trying some of these. Example 3. Go ahead, read this and underline whatever you think is important. But first, go ahead and read it because I don't really feel like reading to you anymore. I believe you can do it. Okay, so cell phones, that's all your information for it. Things that I thought were important were underlined, and then I also just wrote them using their variables. So the mean is 63, the standard deviation is 11, and the n is 100. One of the things that it asked me to do is to find the mean. The other one, the standard error, which is like the standard deviation of the sampling. So I need x bar, the mean of x bar, and we know that it's the same number, so that's also going to be 63. And then your standard deviation of x bar, also known as your standard error of the mean. You're going to get a lot more about this a little bit later, so don't stress out about that. But it's super duper important and going to come into practice a little bit more. So that's going to be 11 over the square root of 100, which is 11 over 10, so 1.1. Now, they also told me to create a graph for this, so I'm going to go kind of like a number line. I know that the mean is always in the middle, and for us the mean was 63. And then we're going to have 1, 2, 3 to the right, and 1, 2, 3 to the left. And this is all about the mean of 100 phone bills. I'm taking the time to write this because on a quiz, if you don't label, I'm probably going to take off a point in my life. So here's what we know. Standard deviation is 1.1. So from the mean, I'm going to add 1.1 to that and get 64.1. That's how I get my next number. So if you can think of the standard deviation as kind of like your scale, but instead of starting at 0, you're going to start at whatever the mean is. So you go 1.1, then you're going to add another 1.1, and you're going to get 65.2. Then another one, 66.3. That's the positive side. Then you're going to subtract as well. So if I subtract 1.1 from here, I believe I'm going to get 61.9, and then subtract another one, you're going to get 60.8, and another 1.1, 59.7. I know that the highest point is always at the middle, so I just go up, and then there's my highest point. I also know that my inflection points happen at 1 point away, so 1 standard deviation away from there. And it's symmetric, so I'm going to do about the same size on this one. I know that the bell curve will look kind of like an upside down parabola starting off, and then inflection means you're going to change directions a bit. So instead of going down, that's where you should start going out and approaching that wonderful axis right there. There you go. That's how you graph it. Take a moment, if you would please, and try example 4 all by yourself, and then press pause while you do that. Unpause when you're ready, because I'll probably just show you how it's supposed to go after that, and then that'll be about it. Thanks. All right, check me, check yourself. These were the same numbers, of course, and then for this one, 18 divided by the square root of 4 gives you 9. I started off at the middle at 135, and then I went by 9s because that's my standard deviation. So 9 plus 9 plus 9, minus 9, minus 9, minus 9. Highest point is still at the middle, and then my inflection points will occur 1 standard deviation away. So I made my bell curve, and then I just went out. And again, you're approaching, but you're not actually going to be touching this axis. So check yours. Also, one other check, make sure that you labeled it as well. When I wrote BPM, beats per minute. Other thing though, just to notice, this was normally distributed already, so that's why it's okay that my sample size was only 4. It's normally distributed. All right, let's keep it pushing. Last one for us. Now, let's talk about probability now that we know a little bit more about the central limit theorem and how to use it for whether it's normally distributed or not. So we can find z-scores from these, and it's pretty much the same formula that you've learned before. It's the value minus the mean divided by the standard deviation or standard error. And that's your formula. Another thing you're going to want to make sure, if you haven't memorized it yet, memorize this formula. So example 5. The graph shows the length of time people spend driving each day. You randomly select 50 drivers, so that seems important. I'm doing 50 drivers. That tells me that my n is 50, which is greater than 30, so it's okay even if this is not normally distributed. And those 50 drivers were between the ages of 15 to 19. Do I care about that? I kind of do, only because that's telling me that that's where I want to look for this chart. So, because right here, this is telling me that the average speed in driving each day by age group, for the age group of 15 through 19, that average is 25 minutes. What else is important here? I want to find the probability of the mean of the time spent driving each day. That is between, so I want the probability that x is between two numbers, 24.7 and 25.5 minutes. Assume, this is also important, that the standard deviation is left-handed struggles, 1.5. Yep. 1.5 minutes. Thank you for your patience. Okay, so what's the first thing that you need to do? Well, the first thing that I would like to do is, because I'm looking for the samples, I need to find my samples under this one. So, take a moment. I know that my sample mean, dang it, that's highly irritating, is going to be the same 25 minutes. I also know that the error, because that's what I'm going to need for this formula, is going to be 1.5 divided by the square root of how many were in my sample, 50. So you can use your calculator for that one, if you would please, and then you will find that that's going to equal about 0.21213. All right, what am I looking for though? So based on this probability part, if I drew a curve, you can imagine that being not as ugly as it is. I know 25 is in the middle because that's my average, and I'm trying to find it between 24.7 and 25.5. Not trying to scale, obviously. I want the probability of landing in this area here. So based on just that, though, like looking how close they are to the mean, it should be a pretty big number. If it was further out, it'd be pretty big as well, but I want this whole entire area. So what do we need first? Well, what I would love for you to do right now is to find your wonderful z-scores for each of these. So you have that formula. Use it right now. So for the first one, I'll do the first one with you kind of, or you can leave me and continue. The first one is going to be 24.7 minus, what was the actual average, was 25 over the standard deviation. So over 0. That's why we had to find that number, 21213. So if you use your calculator, you're going to get negative 1.41. And then for your other z-score, because you also need this boundary as well, you will have 25.5 minus 25 over that same standard deviation. And then for this one, your z-score, I know you can't see it, give me a moment. Your z-score is going to be 2.36. Delightful. So in Z language, here's your 0. You want to have negative 1.41 and 2.36. And this is the area that you're looking for. Okay. So you can use your charts if you would, please. And what would you do? Well, you just had an assessment on this. So let's see if you remember. What we can do is we can take the whole area to the left of P of 236. And then, so the P of 2.36 by looking it up by z-scores. And then subtract this area to the left of it, of P of negative 1.41. So looking these up on your wonderful Z-chart, G-chart, gangster, you can do that and you'll have 0.9909 minus, and then on this one for the chart, it's 0.0793. That's 0.9116. Or you can also say it is about 91%. There you are. All right. Thank you so much for joining me. Enjoy doing your extra practice problems on this. Thank you.